In this video tutorial, we will be covering some very closely related and intertwined topics. We will be covering abstract data types, collections and lists, and allocating memory on demand. These ideas are very intertwined, so you may want to flip through the video. Abstract data types. This is what the CIBC logo looks like. This is what the Chase logo looks like. And here's the Agricultural Bank of China's logo. Notice anything similar? Well, no, not really. But let's look at their ATMs. Notice anything similar now? Well, yeah, they all look super identical. Every ATM looks alike. It doesn't matter what company made it, what country it's in, or what year it's from. That's good for us as users, because that means that when I go to use an ATM, I know exactly what to expect and receive. I know where to put my card in, where the cash comes and goes from, and that's about it. I shouldn't have to worry about the make of the cameras they use, what security protocols are maintained, the reliability of their internet connection, their license to use the images on the screens, the longevity of their magnetic card reader, how many drawers are used to store the cash, when the drawers are cycled out, conflicting dependencies using Python to run some services and C to run others, the intricacies of how the money is authenticated, the wear on the bolts used to secure the ATM to its spot. As you can see, there's a lot to worry about. But how the ATM works internally is all hidden away from me, and I only need to care about the few things I interact with. There's this kind of contract for what I expect and what is delivered. All I need are the insert card, deposit, withdraw, and receive card functions, and I'm happy. This kind of relationship is useful for everybody. That's why, as computer scientists, we have abstract data types, or ADTs for short. These are data types that have their implementation abstracted away from the user. Just like how I don't need to know how an ATM runs, I don't need to know how the ADT is implemented. I just know what operations the contract says they'll deliver. Collections and lists. What happens when we have lots of like-typed items we'd like to group together in some way? Well, we can put them into a collection. Collections are just a general way of saying a group of similarly typed items. Let's say we have a group of people, all waiting in line to enroll into a full class. The first person there should be the first to get a seat if one opens up. Expanding on this logically, the next person there should be the second, the third person the third, and so on and so forth. We can take a bunch of like-type objects, students in this case, and group them together into a wait list, an ordered list. With specific collections, we can define specific behaviors. Let's look at an example of a collection, a list. Here we can define that there will indeed be an order to the items that are stored. To do this simply, each item will be added to the end of the list. Let's say we were tasked to create this list in C. But hold on. The best method we know so far is to use an array. But arrays have a limit to how much they can store that we need to declare when we create the array. So it's best to plan for the worst case. So what if every single student in the U of T system wants to waitlist into this course? That would be all 13,000 UTSC students, 62,000 UTSG students, and 15,000 UTM students, for a total of, carry the 1, 90,000 students. That's a gigantic list. And what if the universities allow more students to enroll? Well, obviously, this isn't going to be a sustainable model. So we will need to think of a way to create a list that will be able to dynamically grow and shrink in size, so it's just as big as we need it to be. This is what drove the development of the linked list ADT. The linked list. Linked lists are an abstract data type, one of the most common examples we will be working with. Each element of a linked list is commonly called a node. The node contains some data and a pointer of our node type. These are structured such that one node points to the next node in the list. Let's write some code for this structure. First, I'm going to include my standard libraries, so hashtag include. Let's include standard IO so we can print out our elements. And let us have our elements be strings. First, I'm going to build the structure for my linked list node. So we know this begins with type depth struct. So we know we will then create a name for this, linked list node, and open up the parentheses, and open up the brackets. Well, our first element will be a string of the name. And we'll just give it a 1024 size like usual. And the next will be the next node in this linked list. So we can call that struct linked list node. We'll give it the name next, and this is going to be a pointer, hence the star here. It's here. We can give this a more common, easier type name. Let's call it LL node, and that is the skeleton of our structure. It has a element of data within it, so that in this case is our name, and it has a pointer to the next node of the same type, struct linked list node. This will automatically be initialized to null. Now that we have built the struct, let's add the dynamic size functionality. Allocating memory on demand. When you declare variables inside a function, they are local to the function. When the function exits, that memory is cleared. We've already seen this at play, where a function cannot declare and return a string or an array, as they are passed as pointers to local variables. We've already seen this at play, where a function cannot declare and return a string or an array, as they are passed as pointers to local variables. This is where dynamic memory comes in. Dynamic memory allows us to ask for, or in technical terms, allocate, some memory that persists even when the function returns. The memory given to you is stored in a separate area in memory called the heap. This becomes much more flexible than static memory, but also harder to use because you have to manage it. This functionality is core to C, and is accessible through built-in commands such as calloc and free. Let's see how we will use this within C. You can use the calloc function to ask for memory. Its parameters simply determine the total amount of memory to allocate. It returns a pointer to the block of memory. This pointer is the only way to access this block of memory, so make sure you don't overwrite the pointer. When you are done using the memory, you need to manually free it using the free function. It takes in the pointer returned by the calloc call. You can free up memory on reserving it and letting somebody else use it by using the free function on a pointer. With this dynamic memory, we can make a linked list grow and shrink to the exact size we want it to be. We will first focus on the ability to create a list. Then we will focus on memory allocation. Let's code one up for our use for U of T's Acorn waitlist system. Let's create some code from this. From our linked list node before, let's create some code to implement a waitlist. So first I'm going to have to create a waitlist. So how do we use linked lists in C? Well, we need a pointer to a linked list node. So within our main function, I'll just create a linked list node pointer. We will call the element waitlist. And we can just initialize this to null for the start. It will automatically be initialized to null otherwise. So what would be a good thing we can do here? Well, a waitlist that's manually added in a person first. Waitlist equals calloc. We're going to create one node. We can use the size of function to know exactly how many bytes we'll need for the linked list node. So we have allocated away a chunk of memory that's the size of one linked list node. Now let's populate this node. Well, the string library allows us to use string copy. We can copy into waitlist arrow name. And let's put Angela in this list. Okay, and then we need to make sure our next is null. That'll automatically be initialized for us, but for just good measure, let's do it. Next equals null. So this will be our first element of our node. Let's create a print function to make sure this works. We will create a void function. I'll print our list. It'll take in as a parameter a linked list node head. We will keep track of where we are with a current node. So we can create an LL node star, a pointer. Current, cur is short for current. And we can just use head as our starting point. Then, while we're not at the end, okay, so how can we check if we're at the end? Well, if our current is null, that means we have nowhere else to go. We will be at the end of the list when our current is null. So while our current is not null, we can perform some actions on this. We can print out what we have in here. Let's print out the string, and let's print out the pointer just to make sure it's not null. and we will just need to put in the string here, cur name, cur next. Okay, so I'll print out the name of the next. And what do we need to do next? Well, we need to move down our list whenever we are done with our element. Cur equals cur. And this is the simple skeleton of how we can iterate over a list. We usually would use cur to a current element, shorthand cur, to keep track of where we are in this list. While we are not null, we can perform some kinds of action, in this case printing, and then within the while loop, we're going to want to move down the next element so we don't stay in an infinite loop. Let's compile this. Okay, I forgot to include the standard library. So let's include that to try to get rid of some errors. Great, we've compiled. Now we can run our a.out and see nothing was printed. That is, of course, because we forgot to use this function. Let's print out everything in our waitlist. Alright, let's recompile. And there you go. We have printed out Angela, and then we know the next element there is nothing, nil, as this compiler has shown us. So we have the first element of our list. Let's try adding some more elements to this list, and let's try adding them to the end of the list. Okay, how would we really do that within this code? Since we're going to be adding elements repeatedly, it'll be a good idea to create a helper function. This helper function can just return void, and we'll just say add to list, or add. It'll take in our linked list, and it should probably take in a string for the name. Now, like before, we will start with the current element that we are at. Whoops. And what do we do after that? Well, we should iterate over the whole thing, over the whole list. And let's think, what is going to be the work we are doing? Before we just printed, what's the work in this case? Well, we're going to add to the end of the list, so we should check if we are at the end of the list. So how can we check if we're at the end of the list? Well, the next element is going to be nothing if we're at the end of the list. So we can say, well, cur next does not equal null. Okay, what can we do within here? Well, let's create some aliases first. We now know that the current element we're at is the last node. So I'm just going to create a pointer to here, just so I can use the word last instead of cur. I know the next element is where I want to put in my new node. This is array pointing to null, so that means I can use calloc, one size of L node, and I will allocate away some memory to create a new element. Okay, how do I get some information in here? Well, I can use my string copy function. And of course, I'm going to want to replace this name. And once again, for good measure, I'm just going to set the next to null, even though it's going to be automatically set for me. Okay, what do I do once I'm outside of my while loop? Well, I'm going to want to move down my list. Sorry, outside of my if statement, inside my while loop. I'm going to want to move down my list. Okay, let's compile this. Oops. Okay, let's add to a list. I'm just realizing now that I made a few bugs in my previous code. First is I checked the incorrect statement. I checked if cur next does not equal null when I should have checked if cur next is null. The second was that I just didn't put the next elements here because I said last next is my new node. So I was updating my last element before instead of my last next element, the new element I'm appending to the end of this list. On the right, we can see that this code now works. So let's add a few more people to this list. I will add Angelo. I will add Angelina. I will add Angelique. And I will add Angeletta. Let's save this, compile it, and run it. So it looks like our list is working. We first have Angela, and then we check that that works. Then we have Angela, then Angelica, then Angela, then Angelina, then Angelique, then Angela, Angeletta, all within the correct order. So that is how we build our linked list for the waitlist for UOT's Acorn system from scratch in C. Now, let's bring some concepts back. ADTs. What we have declared here is in essence an abstract data type. We have defined a linked list, and all you need to know is that we give you an add and a print list function. All you have to do is create a list, and you can add whatever elements you want to a list and print it out, and we handle everything. You don't have to care about all these details. You don't need to know all this code is here. You'll actually be just as well off if I just hit that. As long as the code in there works perfectly, then we are fine. I can add to a linked list any name I want to, and it will be appended to the end. And I can print out any linked list I want to. All I interface with are the add and print list commands. I do not care whatsoever about the implementation within the functions to make my code work. These implementation details have been abstracted away from me, and I'm perfectly fine as the user, because all I know, and all I need to know, is that my add works and my print list works.